All right, geometry, we're going to be learning about section 10.3, which is applying properties of chords. We're going to be looking at several of our new theorems in this section dealing with properties of chords. So let's go ahead and get started. All right, so here's our first theorem in this section. It says in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So if I have two chords inside a circle that I know are congruent, say I have this chord, let's call it AB, and I have another chord. I know they don't look congruent, but here, let's try to draw more congruent. There. Let's call this CD. Okay, if I know these chords are congruent, then I know their arcs are congruent, and vice versa. If I know these arcs, like arc AB, so if arc AB is congruent to arc, not B, CD, CD, then that implies that chords AB, like the segment AB, is congruent to segment CD. Okay, and then this can also be flipped the other way around. If I know segment AB is congruent to segment CD, then that implies that their chords are congruent to each other. And that's what this theorem is about. Let's look at an exercise. This is actually a pretty simple exercise. So in this diagram, it says use congruent chords to find an arc measure. Okay, so in this diagram, circle A is congruent to circle B, and we know that CD is congruent to EF. So this segment here is congruent to EF here. And we know that the measurement of arc CD is 140 degrees. And it says find the measure of the arc EF. So this arc right here. So we're just applying that theorem that we just looked at. If we know that this arc is 140 degrees and these circles are congruent and their arcs, the chords are congruent, then so are their arcs. Their arcs are going to be congruent. So I can say the measure of, well, CD, let's say this, CD is congruent to EF. Okay, so the measure of arc CD is going to be equal to the measure of arc EF, which is 140 degrees. And that's all there is to that one. Okay, I put these theorems together on the same page because they're practically the same thing. They're just converses of each other, okay? So we have if, where's my cursor? There it is. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. Then you have if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. Okay, well, let's look at this. In this circle here, if I draw in, let's say that's about the center, right there. If I draw in, say that is my diameter, and I draw in a chord that is perpendicular to this one, like that there. So for this first one, it says if one chord is a perpendicular bisector of another chord, then the first chord is the diameter. Okay, so if I didn't know that this was the diameter, but I knew that these chords intersected each other at a right angle, so they're perpendicular to each other, and I also, if I knew this fact right here, that these two segments were congruent to each other, meaning that this is a perpendicular bisector here, then I should know that for this theorem here, it says that this first chord here is the diameter. Okay, so that's what that one's telling us. Now, if a diameter of a circle is perpendicular to a chord, so just like this picture, if I know that I have a diameter and it's perpendicular to a chord, then what we should know about this is the diameter bisects the chord. So it bisects it, meaning it cuts it in half. So like I have marked here already, these two segments are congruent to each other. And also the chord and its arc are bisected. So right here, this arc here and this arc here are going to be congruent to each other. Okay, so like if I have labeled A, B, C, what theorem 10.5 is telling us is that arc AB is going to be congruent to arc BC. That's what the second part, and its arc. Okay, so that's what we are looking at here in these two theorems. So here are a couple of exercises to go along with it. Okay, so what I have here for you on this example that deals with what those theorems we're just discussing is an example about use perpendicular bisectors. On this right here, it says 3 baseball players stand in a field as shown. Where should a fourth player, player X, stand if he wants to throw the ball the same distance to each player? So what we're going to do with this one here is I have steps already planned out here, but first step is just connect all 3 of these dots. So connect here to here and here to here. Okay, that's going to be my next slide. So that's step 1. Step 2, now you're going to do this with a straight edge and a compass. The next step is to, remember we're dealing with perpendicular bisectors, we're going to bisect RS and bisect RT. And if you remember with your compass, how we bisect is we put the pointy end on one of our ends of our segment, and we draw an arc like that, and then go and put the pointy end on the other end of the segment and draw an arc like that. And then we connect those intersections like that, and we find where the perpendicular bisector is, and we're going to draw it through the thing, okay? Then same thing for the segment ST. We're going to draw the perpendicular bisector. And this is what you're going to end up with right here. So that's step 2. Draw RS, the perpendicular bisector of RS and ST. Okay. And then by theorem 10.4, these are diameters of the circle containing RST. So we can draw with this intersection right here a circle containing all 3 of these points. And what we would see is from this point to S, that is the same distance as this point to T and R. All 3 of these are the same distance apart. So that's what we just found. So to be able to find where player X needs to stand, you just find the perpendicular bisector of this segment and this segment, and where those perpendicular bisectors intersect, that's where that player needs to stand. So you have, I've given y'all an exercise just like this in your lesson quiz. So if you don't have your compass and straight edge, then we'll do that at school tomorrow or our next class day together. Okay? All right, guys, I have one more theorem and then one more exercise for y'all, and then you're on your own. What this theorem states is in the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. So there are kind of two things being said about this in this theorem. So if I know that these two chords are congruent to each other, I'm going to say, yes, this chord is congruent to this one. Then one thing I do know, or I should know about this from this theorem, is that they are equidistant from the center. Meaning, if I draw a line from here to there, it's perpendicular. Anytime you're equidistant from something, you are drawing a perpendicular line to the other one. So that's perpendicular to that. And then same here. Okay, so we know that these chords are equidistant from the center. So this line right here and this segment right here are congruent. So another way that this thing can be stated, because it's saying if and only if right here, is if we knew the other way around. If we knew that this segment right here, drawn from the center to the chord, and same goes for the center to the chord here. Let's call this O. If we know those two segments are congruent, then we should know that their chords are congruent to each other. So I'm going to write this in terms of what letters we have here. So if we know this, that AB is congruent to CD, then what we should know is that, let's give this another name, GF. Then we should know that FO is congruent to GO. Okay, so that is one meaning of this theorem, but the other meaning is the other way around. It means if we know that these two segments right here are congruent, then we should know that their chords are congruent that we're referring to in the picture here. And that is it on that one. All right, so here's our last exercise that we're going to do together. It says, in circle A, find the lengths CJ and AK. Given BC equals FG, which equals 16, and AJ equals 5. Okay, so let's look at this. BC and FG. Let's see, BC. This segment right here, that chord, BC is 16. And then FG is also 16. Okay, so we should know something from this theorem right here. Theorem 5.10. We should know, we should know that the diameter DE is perpendicular to BC. Okay, so what that's going to tell us by theorem 10.5, let me just write this out for y'all. This is my train of thought. Diameter DE, we know that's the diameter because it's a chord that goes to the center of the circle. It is perpendicular to BC. That's what this symbol means, perpendicular and upside down T. Okay, so by theorem 10.5, the ones that we just looked at, we should know it says DE bisects BC. And we should know if DE bisects BC, then JB and JC are congruent to each other. I'm going to say JB is equal to JC. And that means what we need to do here is this right here is the halfway through point J is. So cut this thing in half and you've got what JB and JC are equal to. So 1/2 of the whole segment BC is equal to 8. And we're done with that one. We figured out that this segment right here plus this one is the whole chord. And the reason that we know that this thing bisects is because of theorem 10.5. Now on the next part it says also find length AK. Oh, I said CJ and JC, same thing. Now find AK. This one right here isn't so bad either. You just have to think about your theorems that we have looked at. It says we should know this. Chords BC and FG. So I'm going to write this down. This is my train of thought. So chords BC and FG, they are congruent. I could have just said that. BC and FG are congruent. BC, FG. And so by theorem 10.6, the one we just looked at, we should know that they are equidistant from the center of the circle. Okay, so what this means is AJ is going to be congruent to AK. These two segments are congruent. We know AJ is 5, so AK is also going to be equal to 5. And that's it on example 3. So what I have left for y'all is this lesson quiz. It deals with things that we have already dealt with in this lesson, but I will try to remember to go over all of these problems tomorrow in class. Hopefully that'll be the, not tomorrow, but the next time I see you, that'll be the next thing that we do. So I will see you then. Goodbye, everybody.